picture this, right? It's 1985.
Okay, I'm there.
You are a medical researcher in The Hague, in the Netherlands, and you have this theory. You strongly suspect there's a link between keeping pet birds and developing lung cancer.
Wow, pet birds. That's highly specific.
Right. But here's the problem. How do you actually prove that to anyone? Because you can't just, look at an X-ray for this.
Oh, absolutely not.
I mean, an X-ray is clean. You break your arm, the doctor points to the jagged white line on the film, and the diagnosis is totally binary. It's either broken or it's not broken.
Yeah, and it is deeply comforting to have that kind of visual certainty. I mean, human beings are literally hardwired to crave clear, unambiguous categories like that.
Exactly. But when you are trying to link pet birds to lung cancer across an entire population of human beings, there is no single clean X-ray. It's a mess.
You're stepping straight into a jungle.
Yes. You're looking at this mountain of chaotic, overlapping, seemingly contradictory information. You've got people who smoke, people who don't smoke, people who work in factories all day, people with parrots, people with pigeons.
People with pristine lungs who kept birds for 50 years.
Right, and people who are incredibly sick, who never owned a pet in their lives. It is the absolute definition of diagnostic murky waters.
And well, that is the reality of almost all modern scientific inquiry. The real world rarely hands us clean answers.
It just hands us raw data.
Exactly. And raw data is inherently noisy. It's full of bizarre exceptions, these dramatic outliers, and hidden variables that you might not even realize are skewing your entire perspective.
Which perfectly brings us to the core mission of today's deep dive. We are going to figure out how to peer into that murky water and actually see the shapes hiding beneath the surface.
Love that framing.
Yeah. So if you've ever felt completely overwhelmed by statistics, or if you just want a shortcut to being genuinely well-informed in a world that is completely saturated with data, this is for you.
It's a survival skill, really.
It is. We are going to demystify the foundational tools that data scientists use to find the truth. And we are going to do it, I promise, without drowning you in terrifying math jargon.
I think that's a crucial promise to make right up front. There's this pervasive myth out there that you need a PhD in advanced calculus or theoretical mathematics to understand how data reveals its secrets.
And you don't.
You really don't. You just need a solid framework for how to ask the right questions.
Okay, so let's unpack this framework. Our guide for this exploration today is a textbook. But before you fall asleep listening to this, let me tell you, this is a remarkably practical one.
It really is.
It's called Statistical Practice for Data Science, with hands-on illustrations using R. And it's by Nalili, G. Asha, and Haim. The beauty of this source material is its accessibility.
Right. It assumes you're coming in with just basic college-level algebra, nothing crazy.
Exactly. The entire focus is purely on application. We aren't going to sit here and read abstract equations floating in a void.
Thank goodness. The authors made a very deliberate choice to bridge that gap between abstract statistical theory and the gritty reality of real-world execution.
Yeah, and they anchor the entire book in a programming language called R,
which functions as the lingua franca of statistical analysis globally. If you do statistics, you know R.
So we are going to look at how data scientists actually use this language to solve real, tangible mysteries. We're going to circle back and figure out that 1985 bird keeping and lung cancer question.
Oh, we have to.
And we're going to analyze the genuinely fascinating, slightly chaotic, romantic lives of horseshoe crabs on the beach.
One of my favorite data sets, honestly.
It's amazing. And on a highly practical, everyday note, we are going to use statistics to figure out if you, the listener, are getting ripped off on your local babysitting rates.
It's such a brilliant spectrum of examples. I mean, you move from serious medical epidemiology to behavioral ecology, straight down to everyday personal economics.
It highlights how universal it all is.
Exactly. The underlying logic doesn't care if you are studying cancer cells or teenagers watching toddlers. The math just holds true.
Okay, so before we can start finding these hidden patterns, we have to understand the physical environment where data scientists actually do their work. Because, you can't cook a gourmet meal without knowing your way around the kitchen.
Right. You need to know where the knives are.
Where are the knives? Where's the stove?
Well, in the context of our source text, that kitchen is the RStudio environment. The text spends a significant amount of time orienting the reader here, and for good reason, because the environment absolutely shapes the work.
So let's break that down. R is the programming language itself.
Yes. R is the raw computational engine that actually crunches the numbers and processes the data.
But RStudio is something different. It's what we call an integrated development environment, or an IDE.
Yes,
I have to admit, I've always found the term IDE a bit intimidating.
it sounds incredibly technical.
It does. But if R is the raw electricity and the heating elements, RStudio is the stovetop, the counter space, and the cabinets,
Right.
all built around those heating elements to make them actually usable for a human chef.
That is a very functional way to look at it, yeah. The interface is designed specifically to make writing, testing, and executing your R code visual and manageable.
Because otherwise you're just staring at what? A black screen.
Right, a blank, blinking cursor in a black terminal window, which is miserable.
So the textbook breaks RStudio down into 4 specific panes. I don't want to get bogged down in the geography of a computer screen, but let's just trace the workflow of this kitchen really quickly.
Sure.
First, you have your source pane. This is your recipe book. This is where you write down the exact steps you want to take.
Like, take this data set, filter out these specific rows, apply this mathematical transformation.
Exactly. You aren't actually cooking yet. You are just meticulously writing the recipe.
And what makes that recipe book so vital is that your script is a permanent, shareable record of your intentions. It's written down.
Right. Then you have the console pane. That's the actual stove. When you take a line of code from your recipe book and hit run, it executes right there on the stove, and the raw output pops out.
You see the immediate result of your cooking.
Yep. Then the environment pane is your pantry. That's where you can see all the ingredients, the data sets and variables you currently have prepped and ready to use.
Your chopped onions, your measured flour.
Exactly. And finally, you have the plots pane. That's the plating station. When you tell the software to generate a beautiful, complex scatter plot, it renders visually right there.
And seeing all 4 of those elements, the code, the execution, the stored data, and the visual output simultaneously, is what makes an IDE so incredibly powerful.
It all happens in one place.
Yes. But we have to ask a deeper question here. And the textbook hammers this point home relentlessly.
Oh, I know what you're going to ask.
Why use a script-based coding environment at all? Why not just use a standard spreadsheet program? Everyone knows how to use them. You can just click, drag, highlight some cells, make a chart in 5 seconds. Why force people to sit there and write lines of code?
I feel like this is the great divide in modern office work right now. Why type code when I can just click on a column and hit sort?
Well, the answer comes down to perhaps the single most sacred word in all of scientific inquiry.
Reproducibility.
Reproducibility. The idea that if I perform an experiment or run an analysis on some data, you should be able to look at my work, do the exact same thing, and arrive at the exact same result every single time.
Okay, so imagine you are managing a massive data set in a spreadsheet. Say it's customer data for your company.
Right, thousands of rows.
Thousands. And you notice some errors. So
Yeah.
you sort a column, you manually delete 50 rows that look corrupted, you copy-paste some missing values from another sheet.
You color a few cells yellow to remind yourself to check them later.
We've all done it. You save the file, you build a nice chart, and you present your report. 6 months later, your boss asks you to update that report with new data.
Or worse, an auditor asks you to prove exactly how you arrived at your final numbers.
Oh, I'd be terrified. There is absolutely no permanent record of the exact sequence of clicks, drags, and manual deletions I made 6 months ago.
None.
I couldn't retrace my own steps perfectly if my life depended on it, let alone explain it to a hostile auditor.
And that is the nightmare of click-based analysis. It is entirely opaque. But with an R script in that source pane we talked about, every single manipulation you make to the data is permanently documented as a line of code.
You don't alter the original spreadsheet at all.
Never. You don't alter the raw data file. You write a script that imports the raw data, cleans it, and analyzes it.
So anyone in the world can take your original raw data file, run your script, and watch the software replicate every single step automatically.
Exactly. To arrive at the exact same endpoint. It is the ultimate paper trail.
And the textbook gives this incredibly fascinating, almost philosophical example of just how far this concept of computational reproducibility goes. It introduces a function called set.seed.
Ah, yes. This is a brilliant illustration. So often in data science, we need to generate random numbers.
Like why, though?
Well, you might need them to simulate a hypothetical data set, Or maybe to randomly assign patients to a placebo group versus a treatment group in a medical trial.
Okay, that makes sense.
And R has built-in functions to spit out random numbers instantly.
But wait, if I'm trying to make my work perfectly reproducible so you can get the exact same result as me, how does that work if I am injecting literal randomness into the process?
It seems like a paradox.
It really does.
Mhm.
Because if I run a script that generates 10 random numbers, and then you run my script on your laptop in another country, you're going to get 10 completely different random numbers. Our results diverge on step 1.
Which would utterly destroy the reproducibility.
Exactly.
The solution lies in understanding that computers, by their very nature, cannot generate true, pure randomness.
Like a rolling die.
Right, or a collapsing radioactive isotope. Computers run on logic and strict algorithms. So when a computer generates quote-unquote random numbers, it is actually generating pseudo-random numbers based on a highly complex mathematical formula.
So it's basically faking it.
In a sense, yes. And every formula needs a starting point, right? An initial value to kick off the calculations.
Okay.
If you use the set.seed function before you ask for random numbers, and the textbook uses the specific example of typing in set.seed, parentheses 76543, you are forcing the computer's internal random number generator to start at that exact specific mathematical coordinate.
So by choosing that completely arbitrary number, 76,543, I am basically anchoring the universe for my experiment.
That is a very poetic way to phrase it, but yes, it captures the mechanics perfectly.
Wow.
By setting that specific seed, you guarantee that the sequence of random numbers the software spits out will be identical every single time the script is run on any machine anywhere in the world.
It looks random to the statistical models.
But the specific sequence is permanently locked in for anyone who uses that seed.
That is so cool. And if you are managing information in your life or building reports at your job, grasping this concept of a reproducible workflow just feels like a superpower.
It really is.
The text even mentions tools built into this ecosystem like Quarto or R Markdown.
Yeah.
These are formats where you literally weave your computer code and the written English paragraphs of your final report into one single document.
It merges the kitchen and the dining room, to borrow your earlier analogy.
Well, exactly. So your code processes the data, generates a chart, and drops that chart directly into the document you hand to your boss.
Right.
If your boss comes back a month later and hands you a completely new spreadsheet of updated data, you don't have to spend 5 hours redoing all your manual clicks and copy-pasting new charts into a Word document.
No, you just update the raw data file, hit run on your script, and the entire written report, charts and all, updates itself in 3 seconds. It completely eradicates repetitive manual labor. It frees the human mind from the tedious mechanics of data processing, allowing you to focus your energy on what actually matters, which is interpreting the results.
Okay, so we are comfortable in our digital kitchen. We understand the workflow. But what do our actual ingredients look like?
The data itself.
Right, because data doesn't just float around as a mystical cloud of numbers. Before we can analyze it, we have to shape it. We have to organize the mess.
We do, and a significant portion of early data science is simply understanding how a programming language like R fundamentally understands the structure of information.
Okay.
The textbook outlines the specific data structures that form the absolute building blocks of everything we will do later. There are 4 main ones: vectors, matrices, lists, and data frames.
Let's start at the absolute ground floor. Vectors.
A vector is the most basic, fundamental structure. You can think of it as a one-dimensional array of data. It's just a single line of items.
Oh, yeah.
But there is a strict, unbreakable rule. Every single element inside a specific vector must be of the exact same data type.
Wait, what does that mean in practice?
Well, it means you can have a numeric vector, for instance, a list of ages, 12, 15, 22, 45, all numbers.
Got it.
Or you can have a character vector, which is a list of text strings, New York, Los Angeles, Chicago. Or a logical vector containing only true or false values. But you absolutely cannot mix numbers and text in the same vector.
So, if I try to make a vector that has someone's name, like Sarah, right next to her age, 28, the system will reject it.
Yes, or rather, it will aggressively try to fix your mistake by forcing the number 28 to behave like a piece of text.
Oh, treating it as the characters 2 and 8 rather than a mathematical value.
Exactly, which will completely ruin any math you try to do on it later. A vector demands purity. It is a single column of uniform data.
Okay, I see why that's mathematically clean, but it seems incredibly restrictive. What if I scale that up? The text mentions matrices.
A matrix is simply taking that one-dimensional vector and expanding it into two dimensions. It has rows and columns. It looks like a grid.
Like a basic spreadsheet.
Right. But that strict rule of purity still applies. Every single cell in that entire matrix must be of the same type. It is all numeric, or it is all character.
Which, again, sounds great for a theoretical math problem, but is functionally useless for the messy reality of human data.
How so?
Well, imagine trying to run a business. If I have a spreadsheet of my customers, I don't just have numbers. I have a column for their age, which is a number. I have a column for their email address, which is text. I have a column for whether they are currently subscribed, which is true or false.
Right.
If I put that in a matrix, the software is going to panic.
Exactly. And that severe limitation is why the most important data structure for any analyst, and the one the textbook focuses heavily on, is the data frame.
The data frame.
Yes, a data frame is R's version of a standard spreadsheet table. It resolves this exact problem.
It lets you break the purity rule.
In a controlled way, yes. A data frame allows you to have completely different types of data in different columns. The only strict requirement is that every column must be the exact same length.
Oh, I see. So column 1 can be my pure numeric vector of ages. Column 2 can be my pure character vector of email addresses. Column 3 is my logical vector of subscription status.
Right, they're all separate, pure vectors.
But the data frame binds them together horizontally. So row 5 reads across all those different vectors to represent the complete, multifaceted profile of one single customer.
That is precisely how it works. And to illustrate this, the textbook utilizes some wonderful data sets built directly into the software.
Yeah, I love these.
One of them is simply called cars. It is a rudimentary data frame that tracks the speed of cars and the corresponding distance it took them to stop.
I was looking at the summary of this data set in the text, and I actually had to do a double take.
Oh, the speeds.
Yes. The maximum speed recorded for any car in this entire data set was 25 miles per hour.
Barely moving by today's standards.
Exactly. And at that absolutely breakneck speed, the maximum stopping distance recorded was 120 feet.
It provides a rather stark historical snapshot.
Right. The data was recorded in the 1920s. Imagine driving 25 miles an hour, hitting the brakes, and traveling almost half a football field before you come to a full stop. It really paints a picture of what early driving was like.
A terrifying picture.
Truly. But structurally, this car's dataset is a classic, simple data frame. It has two columns, a numeric vector for speed and another numeric vector for distance, which is the starting distance.
The text also introduces a more industrial example, a dataset called wire bond. This comes from a study at a semiconductor manufacturing plant.
Okay, shifting gears from old cars to tech.
Right. The engineers wanted to measure the force required to break the tiny wire bonds on a semiconductor chip. So for every test, they recorded 3 distinct variables: the pull strength, the wire length, and the die height.
3 different columns of measurements, all bound together in a single data frame.
Exactly.
Now, let's say I'm an analyst. I get hired by this semiconductor plant. They email me the wire bond data frame, and I load it into my pristine RStudio kitchen. What is the very first thing I should do?
Before you run a single line of mathematical analysis, before you try to draw any charts or graphs, you must run a specific diagnostic function called STRSTR.
STUHAR, which stands for structure.
Correct. The strife function gives you an immediate diagnostic readout of the anatomy of your data frame. It will tell you how many rows you have and how many columns.
Good.
But far more importantly, it tells you how the software has interpreted the type of data hiding inside each of those columns. Is it treating column 3 as an integer, a continuous number, a string of text, or a factor?
Why does that matter so much, though? If I can look at the data and see it with my own eyes on the screen, why do I care how the computer categorizes it in the background?
Because computers are dangerously literal.
Fair enough.
They lack any human context whatsoever. And failing to check the underlying structure of the data is arguably the most common and most disastrous mistake people make when they first start working with data.
Really, the most common.
By far. Consider a data set of real estate listings. One of the columns is the zip code of the house. Now, to a human being, what is a zip code?
It's just a label. You know, Beverly Hills 90211. It just tells me where the house is geographically located.
Right. It is a categorical variable. The fact that 90210 is numerically larger than a zip code in Manhattan, like 10012, does not mean the Beverly Hills zip code is mathematically greater or worth more than the Manhattan one.
Right. It's just a name constructed out of numbers.
But the computer doesn't know about the U.S. Postal Service.
Oh, no way.
Exactly. The computer imports that column, scans down, sees nothing but digits, and inherently assumes, this is a continuous numeric variable. I can do math on this. If you skip running the strive function to check how the computer interpreted it, you might accidentally ask the software to calculate the average zip code for all the houses sold in America last year.
But what would happen? Does it crash?
No, it doesn't crash.
Yeah.
The software would dutifully add up millions of zip codes, divide by the total number, and proudly hand you an average zip code, let's say 54,321.
Which is an entirely meaningless statistic.
Completely devoid of reality. But if you aren't paying attention, you might put that meaningless number into a shiny slide deck and present it to the board of directors.
And get fired.
Probably. To prevent this, you have to look at the structure, identify that the computer is confused, and explicitly tell it to treat those numbers as distinct categories. You have to coerce the data using a function called as dot factor.
So you are stepping in and acting as the translator between human context and computer logic. You are saying, stop treating these digits as values on a number line. Treat them as separate buckets. Treat them as labels.
It is a critical intervention. And this logic bleeds into almost every type of data we collect.
Oh, like what else?
Think about a customer satisfaction survey, where 1 means strongly agree and 5 means strongly disagree.
Oh, right. Those aren't real numbers.
They are just ranked categories. Or think of machine part ID numbers or color codes represented by digits. If you don't use as dot factor to correct the structural interpretation of your data frame, your entire downstream mathematical analysis will be built on a fatal flaw.
That is such a vital warning. The math will always execute perfectly. The computer will always give you an answer. It is entirely your responsibility to ensure the question you are asking actually makes sense based on the structure of the ingredients.
Which serves as a perfect conceptual bridge to the next phase.
Okay.
Once the data is properly organized and structured, we have to understand the mathematical laws that govern how those ingredients behave. We move from the realm of data management into the realm of probability.
Right. And the textbook starts with the absolute foundation of probability, which is discrete, random variables. I like to think of this as finding the certainty inside of uncertainty.
That's a good way to put it. But to ensure we are on firm footing, let's clarify the terminology first. When statisticians use the phrase random variable, they do not mean a variable whose value is utterly chaotic and unpredictable.
Okay, what do they mean?
A random variable is a variable whose possible outcomes are determined by a specific, defined probability distribution. And the word discrete is the key here. Discrete means we are dealing exclusively with things we can count.
Whole numbers. Distinct entities. You can have one customer walk in or two customers.
Yeah.
You can't have 1.4 customers walk into a store.
Exactly.
You can't have a third of a coin flip.
Right. The set of all possible values a discrete random variable can take is strictly countable. It might be a finite set, like rolling a 6-sided die, where the only possible answers are the whole numbers 1 through 6. Or it might be infinitely countable, like trying to count the number of stars in the universe. But crucially, the values move in distinct, separate integer steps. There is no fluid sliding scale between a 1 and a 2.
Okay, so the textbook introduces the simplest, most stripped-down model for this kind of countable data first. It's called the Bernoulli distribution.
Named after the prominent Swiss mathematician Jacob Bernoulli, the Bernoulli distribution is the elegant mathematical representation of a single binary event. Yes or no, success or failure, a 1 or a 0.
The most famous example is flipping a coin. If I have a perfectly fair quarter, the probability of quote-unquote success, which we can arbitrarily define as the coin landing on heads, is exactly 0.5.
Yes, but it is important to note that a Bernoulli trial does not require a perfectly balanced 50-50 split.
Oh, really?
Yeah, the textbook points out that if you have a weighted, biased coin where the probability of landing on heads is 0.75, that is still governed by the Bernoulli distribution.
Okay, so it just has to be two options.
The only strict requirement is that there are exactly 2 possible outcomes, and the underlying probability of success, which statisticians often refer to using the Greek letter pi, or simply p, remains a fixed, constant value for that single event.
Okay, so Bernoulli is flipping one coin, one time.
Mm.
But the real world is rarely that isolated. What happens when I am not just looking at one isolated event, but I am evaluating a whole system of parts? What if I flip 5 coins and want to know the total number of heads?
That scales us up to the next model, the binomial distribution.
Binomial.
The binomial distribution is simply the sum of multiple independent Bernoulli trials conducted under identical conditions.
So flipping 5 quarters and counting the total successes.
Precisely. Or, to ground this in the highly practical engineering example used in the textbook, imagine you are managing a factory floor.
Okay, I've got my hard hat on.
You oversee a complex manufacturing machine. This specific machine relies on 4 distinct, independent internal components to function. Based on historical testing, you know that the probability of any single one of those components operating successfully for a full day is 0.85 or 85%.
Okay, so each individual component inside that machine is its own little Bernoulli trial. It either works for the day, which is a 1, or it fails, which is a 0.
Correct. But as the factory manager, you don't care about a single part in a vacuum. You care if the whole machine runs.
Right, I just want the product out the door.
Now, in the textbook's specific scenario, this machine is designed with redundancies. The entire system will continue to operate as long as at least one of those 4 components is working.
Wow, robust machine.
So we use the binomial distribution to model the total number of working components across all 4 trials.
Wait, let me try to puzzle through the math on that. If the machine works, as long as at least one part functions, and I need to find the total probability of success, doesn't that mean I have to calculate the exact probability of exactly one part working?
Yep.
And then do a separate calculation for exactly 2 working, and then exactly 3, and exactly 4, and then painstakingly add all those massive fractions together? That sounds exhausting.
You certainly could do it that way. The math would hold up. But there is a much more elegant, powerful shortcut built into the laws of probability.
I am all about shortcuts.
A foundational rule of any probability distribution is that the sum of all possible outcomes must equal 1, or 100%.
Right. Something has to happen.
Exactly. So instead of calculating the probability of 1, 2, 3, and 4 successes and adding them up, we can look at the other side of the coin. What is the only possible outcome where the machine completely shuts down?
Oh. If exactly 0 components work. If all 4 fail simultaneously.
Right. So we calculate the absolute worst-case scenario, 0 successes, and we simply subtract that probability from 100%.
Oh, that is so clever. We find the tiny sliver of catastrophic failure, and whatever is left over must be the probability of success.
And finding that sliver is easy. If a component has an 85% chance of working, it inherently has a 15% chance of failing.
0.15.
Because the parts operate independently, the chance of all 4 failing at the exact same time is 0.15 multiplied by itself 4 times, 0.15 to the 4th power.
Okay, let me look at the textbook's calculation here.
Okay.
0.15 to the 4th power equals 0.0050625.
That is a minuscule number.
Extremely small. So if we take 1 and subtract that tiny decimal, we are left with roughly 0.9994.
Yes.
Meaning, thanks to the redundancy built into the system, there is a 99.94% chance that the overall machine will operate successfully on any given day.
The binomial distribution gives us the exact framework to quantify the reliability of a complex system based entirely on the binary behavior of its individual discrete parts.
That feels immensely practical. Okay, so we have the single binary event, which is Bernoulli. We have the sum of a fixed number of binary events, which is binomial. But the textbook takes us one step further into the world of discrete, countable things and introduces the Poisson distribution.
Named after the 19th century French mathematician Simeon Denis Poisson. While binomial deals with a fixed number of trials, the Poisson distribution is used to model count data over a specific, continuous interval of time or space.
The example they use in the book is a retail bank.
Yes, a classic.
We're standing by the door tracking the number of customers who walk into this busy bank between the hours of 9 a.m. and 10 a.m. Based on years of data, the historical average is that 20 customers will enter during that specific 1-hour interval.
What is genuinely fascinating here is the conceptual leap required to move from the binomial to the Poisson model. Think about the physical boundaries of the 2 scenarios. In our factory machine example, there was a strict, immovable physical ceiling. There were only 4 components in the machine. It is physically impossible to have 5 components work.
Right. The maximum limit is hard-coded into the physical reality of the problem.
But the Poisson distribution fundamentally assumes the events are theoretically unbounded. If the bank historically averages 20 customers an hour, Is it mathematically possible that during our 9 a.m. hour, exactly 0 customers walk through the door?
Yes. I mean,
Hmm.
it would be a very weird, quiet morning, but it's physically possible.
The math reflects that. The textbook walks through the calculation for exactly 0 customers, and
Yeah.
without getting bogged down in the specific exponential formula, the resulting probability is astronomically low, but it exists.
Okay.
Now, flip the scenario. Is it possible that exactly 35 customers walk in?
Sure.
Yes. What about 100 customers? What about 1,000 customers trying to cram into the bank in a single hour?
I mean, practically, they wouldn't fit through the door. But mathematically, there is no rule saying 1,000 people can't decide to go to the bank at exactly 9:01 a.m.
Precisely. Mathematically, the probability just stretches out into infinity. There is no hard cap built into the equation, only a rapidly declining probability as you move further away from that known average of 20.
So it just gets smaller and smaller forever.
The likelihood of 1,000 customers arriving is infinitesimally small, practically 0, but the model accommodates the theoretical possibility.
And I imagine that lack of a hard ceiling makes the Poisson distribution incredibly useful for modeling unpredictable real-world events that happen over time.
It is the standard model for it. Civil engineers use Poisson to estimate how many traffic accidents will occur on a specific stretch of highway in a given month. Publishers use it to model the number of typographical errors on a printed page.
Oh, that's interesting.
Physicists use it to predict how many times a Geiger counter will click when exposed to a radioactive source in a 1-minute interval. As long as the events are relatively rare, independent of one another, and occur at a known constant average rate, the Poisson distribution can model the chaos.
Let me see if I can summarize this entire progression of discrete data with an analogy to make sure it's sticking.
Go for it.
Bernoulli is sitting at a table with a friend and flipping a single quarter one time to see who pays for dinner. It's one discrete binary event.
Correct.
Binomial is reaching into a bag, grabbing exactly 10 loaded dice, rolling them all at once, and counting exactly how many land on a 6. It's a sum of a fixed number of events.
Excellent.
And Poisson is pulling up a chair to an open window overlooking a busy street, setting a timer for exactly 1 hour, and counting how many red cars happen to drive past you. It's an unbounded count over a fixed interval.
That is a masterclass synthesis. You have perfectly isolated the core attributes: the single binary trial of Bernoulli, the fixed cap aggregate of binomial, and the time-bound, open-ended flow of Poisson.
Well, thank you. But the world isn't just made up of things we can count on our fingers or tally on a clipboard.
Yeah.
Customers, machine parts, red cars, those are all discrete.
But what about things we measure? Things like the exact weight of a horseshoe crab, or the precise amount of time it takes for a bus to arrive, or the specific dollar amount of a transaction.
To handle measurements, which are fluid and continuous by nature, we must leave the discrete world behind and transition to the realm of continuous random variables.
So in the discrete world, if we were to graph the data, it would look like individual separate bars or distinct dots. You either have 3 customers or 4 customers. There's empty space between them.
Right.
With continuous variables, that space fills in. The data can take on any infinitely precise value within a range.
Think about human weight. You do not weigh exactly 150 pounds. You might weigh 150.23894, depending entirely on the microscopic precision of the scale you are standing on.
That's a little humbling. Because the data is continuous, the possible values form an unbroken interval on the real number line.
So there are literally an infinite number of possible exact weights between 150 pounds and 151 pounds.
Exactly. And this introduces a mind-bending mathematical reality. Because there are infinite possible precise points, the probability of measuring any one exact specific point, say, predicting that a tree in a forest will grow to be exactly, down to the atomic level, 70.0000000 inches tall is technically 0.
Wait, really? The probability of any exact number is 0?
Yes, because it is one single outcome divided by infinity. So, with continuous distributions, we completely change how we ask questions. We no longer ask, what is the probability that x is exactly 70?
Okay, might as well ask this.
Instead, we ask, what is the probability that x falls within the range between 69 and 71? We calculate probabilities by measuring the area under a curve over a specific interval rather than calculating the height of a single distinct bar.
Okay, that makes perfect sense. And the textbook introduces the 2 most foundational models for this continuous data. The uniform distribution and the famous normal distribution. Let's start with the uniform.
Yes.
The textbook calls it the rectangular distribution, which is a great visual. It's perfectly flat.
The uniform distribution models a state of pure, unweighted randomness within a defined range. It applies when every single possible outcome within that interval is equally likely to occur.
The example the text uses is waiting for public transit.
Yeah.
Let's say you walk up to a bus stop, check the schedule, and you know for a fact that the next bus will arrive entirely randomly sometime between exactly now, which is minute 0, and exactly 10 minutes from now.
It is purely random.
It is equally likely to arrive at minute 1.5
Right.
as it is to arrive at minute 8.23.
To figure out the probability of the bus arriving in any specific window, we just have to calculate the area of a rectangle. Now, we know the total probability of all possible outcomes must equal 1, or 100%. If the width of our entire possible window is 10 minutes, then the height of this flat rectangular distribution must mathematically be 1 divided by 10, or 0.1.
So if I am standing at the bus stop, and I want to know the probability that the bus arrives between minute 4 and minute 6, that is a 2-minute window of time.
Yes.
I simply multiply the width of my window, which is 2, by the flat height of the distribution, which is 0.1. 2 times 0.1 is 0.2. So there is a neat, clean 20% chance the bus arrives in that specific 2-minute window.
It is brilliantly simple. The uniform distribution is elegant and highly functional for modeling pure, bounded randomness. In fact, it is the underlying math used when computers generate those pseudo-random numbers we discussed earlier during the set.seed conversation.
Full circle.
But while uniform is useful, the true titan of the continuous world, the absolute bedrock upon which modern statistical modeling is built, is the normal distribution.
The infamous bell curve.
Yes. If we pull back and look at the larger landscape of human knowledge, the normal distribution is arguably one of the most important concepts in all of mathematics.
It's everywhere.
The beauty of the normal curve is that its elegant, symmetrical shape is defined entirely by just 2 parameters. First, the mean, or the average, which dictates exactly where the highest peak of the bell is located on the number line.
Okay.
And second, the standard deviation, which dictates how wide, flat, or narrow the bell spreads out.
And the textbook introduces a kind of golden rule that applies to every perfect normal distribution, right?
Yeah.
The empirical rule. Sometimes people call it the 68, 95, 99.7 rule.
The empirical rule is a crucial shortcut for understanding how continuous data spreads outwards from the center of a normal distribution. It states that roughly 68% of all data points will fall within exactly 1 standard deviation of the mean, above or below.
Right.
Expand that out, and 95% of the data will fall within 2 standard deviations. Expand it again, and an overwhelming 99.7% of all data will fall within 3 standard deviations.
It creates this beautiful, predictable symmetry. Most people are clustered right in the middle, and the numbers trail off smoothly into the extremes. The textbook uses an incredibly relatable, everyday example to show how powerful this rule is in practice. Local babysitting rates.
Yes, this is a fantastic application of abstract math to everyday economics. The text proposes a scenario where the hourly rates for babysitters in a specific suburban neighborhood follow a normal distribution.
Okay, let's look at the number.
The historical average rate, the mean, is $10.50 per hour, and the standard deviation is $1.25.
So just hearing those 2 numbers and knowing the shape of the bell curve, I can instantly visualize the local economy. If the average is 1050 and 1 standard deviation is 125, I subtract the deviation to get the bottom range, 925.
Yes.
And I add it to get the top range, 1175. So using the empirical rule, I know as a fact that 68% of all babysitters in this entire town charge somewhere between $9.25 and $11.75 an hour.
You have instantly grasped the bulk of the market. But the textbook poses a specific challenge. Let's say a teenager named Jess is applying for jobs. Jess is offered a babysitting gig that pays $12 per hour flat.
Okay.
Is this a good offer? How exactly does Jess's offer stack up against the rest of the competitive market?
Now, obviously, $12 is higher than the average of $10.50, so it's better than average. But to figure out exactly how good it is, the textbook says a data scientist would calculate something called a z-score.
All right.
And this is where I start to get a little lost. Why do we need a z-score? Why can't we just compare the dollar amounts directly?
That is exactly the right question to ask. What we are doing when we calculate a z-score is a process called standardizing the data. We are translating raw reality into a universal statistical language.
Okay, walk me through it.
To find Jess's z-score, we take the specific offer, $12, we subtract the market mean of 10.50, and we divide that difference by the standard deviation of 125.
Let me do the math out loud. 12 minus 10.50 gives us a difference of $1.50. So Jess is making it $1.50 above average.
Correct.
Then we divide that $1.50 by the standard deviation of 125. That equals 1.2. So Jess's z-score is exactly 1.2. Okay, I have the number. But what does 1.2 actually represent?
What that z-score tells us,
Yeah.
definitively, is that Jess's offer is sitting exactly 1.2 standard deviations above the average on the bell curve. Because we know the exact mathematical area under a normal curve, we can take that z-score of 1.2 and translate it directly into a percentile.
Oh, I see.
The text shows that a z-score of 1.2 corresponds to roughly the 88th percentile.
Meaning Jess's $12 offer is higher than 88% of all other babysitting rates in the entire town. It's a fantastic offer.
It is a highly competitive rate. The text also shows how we can use standardizing to work backward. Say Jess wants to be in the absolute elite top tier. Jess wants to charge the 95th percentile rate.
Get that money, Jess.
We can look up the required z-score for the 95th percentile, which is approximately 1.64. We multiply 1.64 by our standard deviation of 125, and we add that to our base average of 1050.
And the result?
The math reveals that the 95th percentile rate is roughly $12.55 an hour. So Jess's $12 offer is great, but falls just short of that elite 95th percentile benchmark.
Okay, I see how it helps us find percentiles.
Yeah.
But I still go back to my question. Why convert dollars into this abstract z-score in the first place? It feels like an unnecessary extra step.
This is perhaps the most profound realization in introductory statistics. Standardizing data into z-scores gives us the magical ability to compare completely different, totally unrelated data sets on the exact same scale.
What do you mean?
A z-score strips away the real-world units. It strips away the dollars or the inches or the pounds.
It boils everything down to standard deviations.
Precisely. Let's say you want to compare Jess's babysitting rate to the height of a black cherry tree in a forest and the weight of a horseshoe crab on a beach.
Okay.
In the real world, comparing dollars to inches to pounds is nonsensical. It's comparing apples to oranges to automobiles. But if Jess's rate, the tree's height, and the crab's weight all have a z-score of 1.2 within their respective distributions.
They are all statistically identical. They all sit exactly at the 88th percentile of their respective worlds. Standardizing is the ultimate universal translator. It lets you find the relative truth regardless of what unit of measurement you're using.
It is the great equalizer in data science.
I have a slightly philosophical question for you, though. We just assume the babysitting rates form a perfect bell curve. Why does everything in nature seem to desperately want to be a bell curve?
That's a big question.
Human heights, SAT test scores, blood pressure, the weight of apples on a tree, suburban babysitting rates. Why does the universe prefer this specific symmetrical shape?
You are poking at the absolute foundation of probability. The phenomenon you are observing is governed by something called the central limit theorem.
The central limit theorem.
To keep the concept accessible without getting bogged down in proofs, the basic idea is this. When a single continuous trait, like the height of a human being or the hourly rate of a babysitter, is the ultimate result of hundreds or thousands of tiny, independent, random factors all stacking on top of each other, the final sum of all those factors will inevitably, mathematically, form a normal distribution.
So it's the sheer volume of tiny variables that forces the shape.
Yes. Think about a babysitting rate. It is not decided in a vacuum. It is influenced by the teenager's age, their level of experience, the parent's disposable income, the distance the teenager has to travel, the number of toddlers involved, local inflation rates, whether the teenager has CPR training.
Wow.
All these tiny, mostly independent variables stack up. And mathematically, when you add up enough random variables, the extreme highs and extreme lows cancel each other out. And the massive majority of outcomes are pulled magnetically toward the center, creating that distinct bell shape.
The central limit theorem acts like gravity for data. It pulls everything toward the average.
That is an excellent analogy. However, and this is a massive caveat that the textbook emphasizes repeatedly, because the mathematical properties of the normal distribution are so convenient and easy to use, novice analysts often blindly assume their data is normal when it is absolutely not.
We want everything to be a bell curve because the math is easy.
Precisely. But not all continuous data forms a bell curve. Wealth distribution, for example. The wealth of a nation does not cluster symmetrically around an average middle class. It is heavily skewed, with a massive cluster of lower wealth at the bottom and a long, thin tail of billionaires stretching out to the right. If you assume wealth is a normal distribution and calculate z-scores, your entire analysis will be pure fiction. This is why we can never trust the raw equations alone. We must visualize the data before we analyze it.
Which brings us perfectly to the next phase of our data journey. We've structured the data in our studio, we understand the theoretical math and the probability distributions, but how do we combine those two things to actually look at the methy real-world data and see if it behaves the way the math predicts? We have to start painting with numbers.
We need to build a visual vocabulary for quantitative data, and the most basic fundamental tool for summarizing a continuous data set is the histogram.
Now, if I glance at a histogram quickly, it looks exactly like a standard bar chart. It's just vertical rectangles. But they're fundamentally different tools, right?
Very different. A bar chart is used for categorical data. Each bar represents a distinct, unrelated bucket, like a bar for people with blue eyes and a bar for people with brown eyes. The bars have space between them because the categories don't mathematically touch.
Okay, so what's a histogram?
A histogram, however, is designed specifically for continuous numerical data. It takes the entire unbroken spectrum of your data and intentionally chops it up into contiguous touching intervals, which statisticians call bins.
Bins. The textbook goes back to our forestry data set for this. The trees data frame featuring 31 felled black cherry trees. The data we're looking at is the continuous height of these trees. The shortest tree is 63 inches and the tallest is 83 inches.
To visualize this continuous spread with a histogram, you might instruct R to create bins covering 5-inch intervals. So the first bin captures every tree between 60 and 65 inches. The next bin catches everything from 65 to 70 inches.
Got it.
The bins sit shoulder to shoulder on the axis. The height of the rectangle drawn over each bin tells you the frequency, exactly how many individual trees fell into that specific 5-inch range.
What is incredibly satisfying about a histogram is that it allows you to test reality against the theoretical math. The textbook shows how you can literally command R to draw that perfect mathematical bell curve and overlay it right on top of the real-world rectangles of your histogram.
Yes.
You can see instantly with your own eyes if your actual 31 cherry trees follow the mathematical ideal or if they are skewed to one side.
It provides an immediate visual check on your assumptions. But histograms have a known vulnerability. They can be highly sensitive to the choices the human analyst makes.
How so?
If you decide to change the width of those bins from 5 inches down to 1 inch, the visual shape of the histogram can change dramatically, sometimes hiding or creating false peaks in the data.
Oh, because you're chopping it different.
Because of this subjectivity, data scientists rely heavily on another visual tool that is much more mathematically rigid, the box plot.
The box plot, or as I remember it from middle school math class where I totally failed to understand it, the box and whisker plot. It just looked like a rectangle with antennas.
They can be unintuitive at first glance, but they are incredibly dense with vital information. A box plot is built entirely on what statisticians call the 5-number summary of your data set: the minimum value, the first quartile, the median, the third quartile, and the maximum value.
Let me make sure I'm mapping this right. If I physically chop down all 31 black cherry trees and I lay them out in a field in a perfectly straight line, ordered from the absolute shortest to the absolute tallest.
Okay, quite the visual.
The median is the exact middle tree, the 16th tree in the line. Half the trees are shorter, half are taller.
Correct.
The first quartile is the tree standing halfway between the shortest tree and the median. And the third quartile is the tree halfway between the median and the tallest.
That is a perfect physical visualization. In a box plot, the main box is drawn spanning from that first quartile to the third quartile. This box is incredibly important because it represents the physical boundary of the middle 50% of all your data.
It contains the bulky average center of the herd, completely ignoring whatever weird extremes might be happening at the very top or bottom.
Exactly. And the physical width of that box is a crucial metric called the interquartile range, or the IQR. The IQR tells you how tightly packed or loosely spread that middle 50% is.
What about the antennas? The whiskers?
Now, those weird extremes you mentioned are handled by the whiskers, the lines extending out from the top and bottom of the central box. But here is the critical part, and where the rigidity comes in. The whiskers do not just arbitrarily reach out to touch the absolute highest and lowest data points in your data set.
They don't.
No. The box plot algorithm uses strict mathematical formulas to calculate what are called fences.
It literally builds a mathematical fence to figure out if a data point has wandered too far away from the herd to be considered normal.
Yes. The math takes the emotion and the visual guesswork out of identifying outliers. To calculate the inner fences, the algorithm takes the IQR, the width of your middle box, multiplies it by 1.5, and extends that distance out from the top and bottom edges of the box.
Okay.
Any individual data point that falls beyond that inner fence is officially classified, statistically, as a mild outlier. If a point is so extreme that it falls beyond the outer fence, which is calculated as 3 times the IQR, it is classified as a serious outlier.
I love that. It stops you from just looking at a spreadsheet and saying, wow, 83 inches seems weirdly tall for a cherry tree. Instead, you can look at the math and say, that tree's height exceeds the calculated upper inner fence. It is objectively a statistical outlier.
The textbook also mentions the stem and leaf plot, which is an older, purely textual way of visualizing the same kind of distribution, where the leading digits of a number form the stem and the trailing digits form the leaves.
Yeah, I've seen those.
It's less common now, but when they use a stem and leaf plot to map the volume of those same cherry trees, the text-based shape immediately reveals a right-skewed distribution, meaning the tail extends far out toward the higher numbers, and it clearly visibly flags one massive freak of nature tree with a volume of 77 as a serious outlier.
But where box plots truly become absolute superpowers is when you start putting them side by side to compare different groups.
Yeah.
And this brings me to, honestly, my favorite data set in the entire textbook, the tensile strength data.
Ah, yes. This is a classic industrial engineering problem and a perfect example of why visualization is mandatory.
Set the stage for us.
An engineering team is testing a new synthetic fabric. They need to know how the cotton weight percentage, the CWP, affects the tensile strength of the fabric. In plain English, how much pulling force does it take to physically rip the fabric apart?
They run experiments on fabric blended with 5 different levels of cotton: 15% cotton, 20%, 25, 30, and 35%. They test 5 distinct patches of fabric for every single level. Now, if I'm a busy manufacturing executive, I might just ask the software to calculate the average overall tensile strength across all the tests, just to get a baseline number for how strong the product is. But if I do that, the textbook implies that single number is essentially a lie.
It is worse than a lie. It is a dangerous obfuscation. An overall average would completely obscure the actual physics of the material. But if you instruct R to draw side-by-side box plots, placing one vertical box plot for the 15% cotton tests, right next to one for the 20%, right next to the 25%, and so on, a stunning, undeniable visual narrative emerges on the screen.
It is so dramatic. If you look at the sequence of boxes moving left to right, the tensile strength steadily climbs. The box for 20% is significantly higher on the graph than the 15%. The 25% is higher still. At 30% cotton, the fabric reaches its absolute peak strength. The box sits high and proud on the graph. But then you look at the box for 35% cotton.
It is an utter structural collapse.
The entire box plot for 35% cotton plummets back down to the very bottom of the graph. It is significantly weaker than almost everything else.
And this is the profound danger of summary statistics. The relationship between cotton percentage and strength here is not a straight linear line. It is curved.
Yeah.
Adding more cotton makes the synthetic fabric stronger and stronger, right up until a critical chemical tipping point at 30%, after which the structural integrity of the synthetic blend is totally compromised, and adding even 5% more cotton actually ruins the fabric.
If that executive only looked at an overall average or assumed a linear relationship, they might mandate that the factory produce 35% cotton fabric, thinking, well, more cotton clearly means stronger fabric, and they would mass-produce a disastrously weak, defective product.
Absolutely.
Seeing the data mapped out in a side-by-side box plot literally saves the company from a catastrophic manufacturing error.
It is an unassailable argument for why exploratory data visualization must always be the very first step in analysis before any models are built or averages calculated.
Okay, so histograms and box plots are incredible for showing us the summary shapes of our data, where the bulky center lives, where the mathematical fences are, how different categories stack up against each other.
Right.
But sometimes a summary isn't enough. Sometimes the relationships in the data are so complex that we need to see every single individual data point to understand what is actually happening.
We need to strip away the boxes and bins and move to coordinate mapping. We are moving to dot plots and scatter plots.
Let's start with the dot plot, which is basically a one-dimensional scatter plot. And we finally get to use the horseshoe crab mating data set. I promised crab romance in the intro, and here we are.
This is a rather famous data set in ecological statistics. Researchers spent time on the beaches studying female horseshoe crabs to understand exactly what physical factors influence their mating success.
The drama of the beach.
Specifically, they wanted to know what caused a female crab to have male suitors, which ecologists refer to as satellites residing nearby in her nest. They painstakingly recorded the color of the female shells, the physical condition of their protective spines categorized as good, middle, or bad, and the exact count of satellite males hovering around them.
To visualize this, a basic dot plot simply draws a single line for an axis and places a dot for every individual crab along that line. It lets us see the actual raw distribution of how many satellite males these crabs attract.
That's the basic version, yes.
But the textbook shows how you can get incredibly layered and fancy with it in R. You can make a dot plot where the crabs are grouped horizontally by their spine condition, and then every single dot is color-coded based on the literal darkness of the crab's shell.
It's beautiful.
Suddenly, you aren't looking at a summary, you are visually parsing out dot by dot. If the darker crabs with pristine spines have more suitors than the lighter crabs with damaged spines.
It allows the human eye to detect subtle interaction effects between multiple variables. But when we want to see the pure mathematical relationship between two continuous quantitative variables, say, two distinct measurements on the same object, we upgrade from the 1D dot plot to the classic 2D scatter plot.
We can go back to our black cherry trees for this. If we plot the physical girth of the trees along the horizontal x-axis and their total volume of wood on the vertical y-axis, we get a scatter plot. Every dot represents one tree.
And what do you see?
The pattern that emerges is unmistakable. It forms a tight, sharply rising diagonal line. As you move right on the axis you move up, the fatter the tree, the more volume it has. It is an incredibly clear, positive linear relationship.
But if you instruct the software to plot the height of the trees on the x-axis and the volume on the axis, the resulting dots are scattered much more randomly across the grid. There is a very slight upward trend, but it is diffuse and cloudy.
A completely different shape.
A scatty plot instantly, intuitively reveals both the strength and the specific shape of the correlation between two measurements.
But the textbook points out a massive, highly practical problem with scatter plots. It's easy when you only have 31 cherry trees. What if you were working for a modern tech company and you don't have 31 data points? You have 10,000 data points or 100,000.
The visual mechanics breakdown.
Right. And what if a huge chunk of those data points happen to share the exact same values? What if I have 500 different crabs in my data set that all weigh exactly 2 kilograms and all have exactly 3 satellite males?
When hundreds of data points share the exact same coordinates on a graph, the software plots them perfectly on top of each other.
Right. If 500 individual black dots are stacked flawlessly on top of each other on a screen, my human eye just sees one single black dot. Of a massive data set of 100,000 users, the entire scatter plot just turns into a giant, unreadable, solid blue blob.
It completely destroys the visual density of the data. You lose the entire ability to see where the actual concentration of points lies, which defeats the entire purpose of the visualization.
But data scientists have a trick to solve this overlap problem, and honestly, the name of the trick sounds like you are making a mistake. It is called jittering.
Jittering is a deceptively brilliant mathematical technique. When you apply the jitter function to your variables in R, the software intentionally injects a tiny microscopic amount of mathematical noise into every single data point's coordinate.
Wait, I need to stop you. We spent all this time making sure our data is pure and structured and our math is exact, and now you are telling me we are intentionally making the data inaccurate just so we can see it better.
Yes, but it is a controlled, mathematically bounded inaccuracy. The noise that gets added is drawn randomly from a uniform distribution. The textbook explicitly explains that the default amount of noise added by the software is carefully calculated.
How careful?
It usually uses a formula like d divided by 5, where d represents the smallest difference between any two original distinct data values, It is just enough mathematical noise to slightly shift the identical points away from each other so they stop overlapping, but it is mathematically guaranteed not to be enough noise to change the overall statistical shape or the fundamental correlation of the massive data set.
It is like,
Mhm.
imagine you are standing 1 inch away from a massive impressionist painting, like one of Monet's water lilies.
Oh, I like this.
Because you are so close, it just looks like a chaotic, overlapping blob of wet paint. You literally cannot see the lilies. But if you take 5 steps back, if you intentionally add distance or jitter between your eye and the precise details of the canvas, the individual blobs of paint resolve, and the true shape and depth of the painting reveals itself.
That is a stunning analogy and perfectly accurate. By adding a tiny bit of space between identical data points, a single solid black dot suddenly expands into a visible cluster of 500 individual points. The true density of the data is visually revealed to the human eye.
The text also mentions a function called smooth scatter, which feels like the ultimate evolved version of this concept.
Yes, smooth scatter.
Instead of drawing 100,000 individual dots, it turns the scatter plot into a fluid heat map where the highest density areas are shaded a deep, impenetrable dark blue, and the sparse outlier areas fade into a light, wispy blue. Between jittering the points and smoothing the densities, you can tame even the most overwhelmingly massive datasets.
It highlights a core, almost philosophical tenet of data visualization. Sometimes, strict adherence to the absolute accuracy of the individual point is actually less important than achieving clarity in communicating the overall distribution to a human brain.
Wow. Okay, we have covered an immense amount of ground. We have graphed continuous numbers, we've analyzed sizes, weights, and heights, we've built histograms, calculated fences for box plots, and smoothed out heat maps. But we have one final frontier to cross.
We do.
What happens when our data isn't a number at all? What happens when we are just trying to visualize a category?
We are transitioning from the quantitative visual tools we've been using over to qualitative visual tools.
And to do that, we absolutely have to talk about the most famous, the most ubiquitous, and perhaps the most infamous chart in the entire corporate business world, the pie chart.
Indeed. If we go back to our horseshoe crab dataset, and we want to show a simple breakdown of the crab's spine conditions, which are purely categorical, good, middle, or bad, we could easily use the pie function in R.
Okay?
The software will generate a circle, divide it into 360-degree proportional angles based on the counts, and you can even instruct it to color the slices using a bright, cheerful rainbow palette.
It sounds so pleasant and standard. Every slide deck I've ever seen has a pie chart in it. But I know data scientists have strong feelings about this. There is a dark side to the pie chart.
There is, and the textbook does not shy away from making this point explicitly. While pie charts are incredibly, almost inexplicably popular in corporate boardrooms and media presentations, virtually all modern statistical textbooks and professional data scientists strongly advise against using them.
Wow, they just hate them.
In fact, for visualizing categorical data, dot plots or standard bar graphs are explicitly preferred for accurate interpretation.
Why is there such hostility toward a simple circle?
It comes down to human biology and cognitive psychology. The human eye and the visual processing center of the human brain are notoriously predictably bad at estimating and comparing angles in two-dimensional areas.
Really?
Yes, and a pie chart relies entirely on comparing angles. If you have a pie chart with 5 different slices, and 2 of those slices represent roughly 22% and 25% of the data, the human eye struggles immensely to see which slice is actually larger just by looking at the angle of the wedge.
The angles just blur together in our heads. It's too subtle of a geometric difference.
Exactly. Our brains are not built to calculate radial geometry on the fly. However, human beings are incredibly good at comparing linear distances. We are exceptionally good at comparing the heights of straight lines standing next to each other.
Which brings us directly to the bar plot.
Yes. If you take that exact same horseshoe crab spine data and simply render it as a standard bar plot, your 3 categories are laid out on the flat x-axis, and the numerical count forms the axis. The bars rise vertically from a completely flat baseline.
And instantly, in a fraction of a second, your brain can see that the bar for the bad spine condition is significantly taller than the bar for the middle spine condition.
There is zero ambiguity.
You don't have to guess about angles. The visual comparison is instantaneous and mathematically accurate to the human eye.
It is a profound lesson in communication. Whenever you read the news or you are handed a corporate annual report, you should be deeply skeptical of pie charts. Very often, whether intentionally or accidentally, they are used precisely because they obscure small differences and muddy the waters differences that a bar plot would make glaringly obvious. Data scientists prefer bar plots because they enforce visual honesty and cognitive clarity.
That is a fantastic tip for navigating the modern world. Beware of the pie chart. It's probably hiding something. Now, before we finish, the textbook introduces one last, highly specialized categorical chart called a spine plot. What exactly is that? It sounds related to the crabs, but it's not, right?
No, it has nothing to do with crab spines. A spine plot is a mathematical generalization of a stacked bar plot, but it is uniquely powerful because, unlike a standard bar chart, it communicates critical information on both the x and y axes simultaneously.
How does that work?
In a standard bar plot, all the vertical bars are drawn at the exact same width. Only the height conveys data. In a spine plot, the width of the bar represents the relative frequency of one category, while the height inside that bar represents the conditional frequency of a second category.
It's like a two-dimensional bar chart that uses area to show relationships. And the textbook illustrates this perfectly by finally bringing us back to where we started, the 1985 Hague birdkeeping study.
Yes, the epidemiology study trying to link pet birds to lung cancer. The researchers compared 49 patients diagnosed with lung cancer against a control group of 98 healthy individuals. They wanted to see if the act of keeping pet birds was a significant categorical risk factor.
So we have two entirely binary categories crossing over each other. Do you have lung cancer, yes or no? And do you keep pet birds, yes or no?
By visualizing this complex crossover data in a spine plot, the horizontal x-axis might represent whether the patients had cancer or not. Because there were 98 healthy people and only 49 cancer patients, the physical width of the healthy bar is drawn twice as wide as the cancer bar.
So the widths instantly show you the relative sizes of the total groups.
Right. But then, inside each of those two bars, they are divided vertically by color to show the proportion of people who own a bird.
Oh, that is brilliant. So, with one single glance at this spine plot, you can visually compare the vertical percentage of bird owners in the massive healthy group directly against the vertical percentage of bird owners in the smaller cancer group, all while your brain keeps the total sample sizes in perspective because of the differing widths of the bars. It is an incredibly dense, efficient way to display complex categorical risk factors.
It allows the viewer to instantly grasp complex relative frequencies and hidden correlations without needing to stare at a dizzying spreadsheet of cross-tabulated raw numbers. It makes the invisible relationship visible.
And that really brings us full circle on this entire journey. We started this deep dive talking about how we expect medical data to be a clean, unambiguous X-ray. We looked at the murky, chaotic world of raw information. But what we've discovered today is that data science isn't just about feeding cold numbers into a supercomputer. It's about making highly specific, deeply intentional choices on how to structure, manipulate, and ultimately visualize those numbers so the flawed, easily confused human brain can actually comprehend the truth.
We have covered an immense amount of conceptual ground today. We walked into the RStudio kitchen, organized our digital environment, and learned why the strict computational reproducibility provided by functions like set.seed is the absolute bedrock of valid, trustworthy science.
We took a mountain of messy data and learned how to structure it into rigid vectors and flexible data frames. We learned the hard way why a zip code must be translated into a factor so the computer doesn't foolishly try to average out our geography.
We traced the arc of probability, starting from the discrete binary coin flips of Bernoulli, moving through the bounded systemic trials of the binomial factory machine, and looking out the window at the unbounded flowing counts of Poisson's bank customers.
And then we crossed over the line into the continuous spectrum. We saw the pure, flat randomness of the uniform bus arrival, and we felt the majestic, inescapable gravity of the normal bell curve, using standardizing z-scores to govern our suburban babysitting rates and compare apples to oranges.
We used histograms to check our reality, and we relied on the strict mathematical fences of box plots to find genuine outliers in cherry trees. And we saw vividly how a simple overall average can completely hide a catastrophic curving failure in the tensile strength of fabric.
We plotted the complex romances of horseshoe crabs on the beach. We learned to intentionally jitter our massive scatterplots to reveal hidden density in the noise. And finally, we learned why true data scientists utterly despise the deceptive pie chart and trust the honest geometry of the bar plot.
It is a profound and immensely powerful toolkit for understanding the modern world.
It really is. And I want to leave you with one final, slightly provocative thought to chew on as you go about your day. We tend to think of statistics and data science as this cold, hard, purely objective field of math. We think the numbers are just the numbers, right? But as we learn today, whether it's using the jittering technique to intentionally add random noise to a graph, just so our limited human eyes can process the overlap, or making the conscious choice to use a bar plot over a pie chart purely because our primate brains are terrible at estimating angles. Data science is actually a deeply human-centric art.
I couldn't agree more.
The numbers do not speak for themselves, they are completely silent. They rely entirely on how we as analysts choose to translate them, format them, and present them to the human eye. So if you go through your week, look closely at the charts in your newsfeed, in your corporate reports, or on your social media. What other objective truths in your daily life are being shaped or perhaps actively manipulated by the visual format they are presented in?
It changes everything.
Ask yourself, who chose to use that pie chart? Who decided to hide the outliers? What happens if I demand to see the box plot? The water of the world is still murky, but now you know exactly how to read the ripples. Thank you for joining us on this deep dive into the architecture of data. Keep questioning the charts, keep looking for the hidden variables, and we will see you next time.